Hello and welcome to today's video. Today we're going to be looking at question 2 of the STEP 2011. So STEP is the sixth term examination paper set by Cambridge University for entry to undergraduate studies in mathematics and mathematical sciences in general. So let's have a look. So we've got here to write down the cubes, then we have to look at some equation, and then I presume at some point we'll have to solve this equation. Here we do, use these results. We've got to deduce some algebraic identities or equations, and then we consider finally some other case, and then hopefully use some of the knowledge that we've gained maybe for a way into solving part 2. So let's start with part 1. So at the beginning I'm just going to paste these cube numbers, and maybe we'll be leaving them later. So let's have a look at part 1. So we have to show that, well, assume first that x plus y is equal to k, and that z cubed is equal to k squared. No, not this one. That's not what we can't assume because we're solving for that. We have to assume this x cubed plus y cubed is equal to k z cubed, and that x, y, z, k are as stated. So what do we do? How are we going to get to this from this? Well, we've got a cubic, x cubed plus y cubed equals kz cubed. But here we have z cubed, so that's good. But the other side, we've cancelled by k somewhere in the process by the look of things, and we've got these x term and x squared term, and no y's. So what we're going to know, we're going to have to substitute for y, probably from this equation number 1 here, and then we're going to hopefully find some way of finding k as well, because as we can see there are no cubic terms in x. So what we can do is just write out x plus y and then cube that, because that seems like a good idea. Then we'll get k cubed, and we can substitute k maybe in and then cancel and we get a k squared. So this seems like a good idea, so let's try this. So if we remember our binomial theorem, this is just 3x squared y here plus 3xy squared plus y cubed. And now we're going to substitute in k for the x plus y cubed. But first, before that, we have to solve for x cubed plus y cubed, and that is going to be x cubed plus y cubed, and then we subtract these two terms from this, which will give x plus y all cubed, subtract, and then we might as well factor out. So we've got an x term in both and a y term, so we could factor out an xy maybe, and then we're going to end up with here we've got obviously an x squared term, so that will appear here, and then here we're going to get an x plus y. The reason why is because another x plus y is just k, so that seems like a good idea. And then we've got our required identity. So now we're going to substitute in here k for x plus y. So we end up with k cubed, and then we're going to subtract 3xy, and then x plus y, but that is nothing but k. And going from here, we have that x plus y cubed is exactly kz cubed, so we can write therefore kz cubed is equal to this. And now we're looking quite good, because we've got here almost every term without a y and k in every term, so we can cancel immediately by k, and so therefore we get z cubed is equal to k squared, and this is going to be 3xy. But instead of writing y, we're going to write from this expression k subtract y, and that is x. So well, actually we want obviously y, don't we? So we want k subtract x, sorry. So we're going to get k subtract x, and then when we expand this out, we're hoping this will be exactly what we want. Well, we get 3xk, and then we've got a negative, but it's 3 x squared. So the first part was rather simple if you can really spot the things that you need to spot. So we need to get rid of the cubic terms, and we need to realize that we've got this identity here. That's what enabled us to cancel, because we are rearranging, and this is nothing but x cubed plus y cubed with other stuff mixed in, the lower powers of x, and then we can factor out here, and then we get our required identity. So it's not too hard if you're used to these types of expressions, but obviously for the majority of the time, not the easiest. So now we have to do something else. We have to show that this weird looking thing, 4z squared minus k squared over 3, is a perfect square, and that we have this inequality here, these three inequalities, that a quarter k squared is less than or equal to z cubed, which is also less than k squared. But we can see this is definitely true. K squared over 4 is definitely less than k squared because k is a positive integer. However, we don't know about z cubed and k squared, so this is the second part, and maybe we could deal with this as the first part. So let's have a look. So we've got here z cubed, but we have to show that this is a perfect square. Now, I know that there's 4z cubed, so I'm going to multiply this last expression here by 4. So multiply, I'm going to call this 1. Multiply 1 by 4. And we're going to get, let's see, too hard to see, 4z cubed is equal to 4k squared. Subtract 3 times 4, which is 12xk plus 12x squared. Now I think, oh, this looks even worse. But then we've got 4z cubed minus k squared, so why not subtract k squared from both sides? Because we want the left-hand side at least to look like this. And then if we can then see that this is actually equal to a square number on the right-hand side, then we will be done. So what we do is we subtract 1 out of k squared, and this is the clever bit, and then we get 12x squared minus 12xk plus 3k squared. Now we have a factor of 3 everywhere here, so that's convenient. So then what we can do is we divide this side by 3, well, we'll divide both sides by 3, but that's what we get here. So we get our required expression, and then we hope that this is going to help us. So we're going to get here 4x squared, subtract 3xk, sorry, is that right? 4xk, isn't it? 12 divided by 3 is 4. So we get 4xk, and then we have to add our k squared. Now, how do we know that this is a perfect square? Well, if we can write it as brackets something all squared, then it will be. But we're led by our noses because we have our left-hand side equal to this left-hand side. So therefore, we must have a perfect square, otherwise they wouldn't ask us to do that. So let's see if we can write it. So we know that 4 squared, 4 square rooted is 2. So we're going to write this as this is a perfect square number. So we're going to write that in brackets. Now, what are we going to write this side? Well, we need to have a k, so we need to have a k, but are we going to have a, if we add these, if k is positive, then we get, obviously going to get 2xk plus 2xk appearing here, so we want the negative side, and it is indeed a perfect square. So, as required. As required. I mean, you might want to write this as n squared, where n is equal to 2x minus k. And of course, because they're all integers, this will be an integer, so it's an integer, so it's a perfect square. Right, now we have to show that a quarter squared is less than or equal to z cubed. Well, how are we going to see that? Well, what do we know about square numbers? Well, square numbers of positive integers, anyway, we know a lot about. They're always positive, and at least, the very least, they're greater or equal to 0. And so what we can say then is that since positive integers are greater or equal to 0, we have that 4z cubed subtract k squared is going to be greater or equal to 0 as well, because this is greater or equal to 0, so this side must be greater or equal to 0. Therefore, we can see that z cubed, rearranging this, is greater or equal to k squared over 4. So that part's done. Great, excellent. So now we have to show that z cubed is less than k squared. Well, sorry, the k squared, yes, k squared subtract z cubed is greater than 0. Well, how are we going to do that? Well, we've got here k squared and a z cubed. So what we want to do is we want to manipulate this expression maybe. So let's have a think. Well, if we just start, so if we want to show something is greater than the other, then their difference has to be greater than 0. So we need to show that k squared subtract z cubed, want to show is going to be obviously greater than 0. Then k squared is greater than z cubed. And that's what we want to show here. Or at least z cubed is less than k squared. So what have we got? Well, we've got here this expression. So we're going to write that down. We have z cubed is equal to k squared subtract 3xk plus 3x squared. So what we want to do is we want to have this, so we need to subtract z cubed and then add this side to the left hand side. Then we'll have k squared subtract z cubed, and we're going to hope that this is going to be positive. So what have we got? We've got 3xk plus 3x, well, it'll be negative 3x squared. Right, so why is this positive? Well, let's see. So we've got here factor out. Again, it seems obvious to factor out. So we get 3x, and then we get k subtract an x. And what do we know about this term? Well, at the moment, nothing much. But if we go back, always look back to what you've been given, because that's the only way you're going to solve a problem. It's the only obvious way you're going to solve a problem. So what you have to do is you have to look back to your x plus y is equal to k. We know something about y, but we don't know anything about the difference of k minus x on its own, but we know that it's equal to y, so we just put that in. But this is 3xy. And why is this useful? Well, because these are all positive integers. Therefore, we have that this expression has to be at least greater or equal to 3, because this could be 1 and 1, but that's certainly greater than 0. And so what we get then is that k squared is greater than z cubed. Great. So now let's have a look back to the question. So we've done all of this, and now we've got to use these results to solve the equation. So this part might be harder, but we're going to use some bounds, hopefully, to, if we can see that k is 20, then we're going to have some bounds on z cubed, because z cubed is a positive integer, so we have a restriction maybe. So let's have a look. So what we've got. So, right, so let's k be equal to 20. So what we're going to do is write the information that we have, we wish to solve, therefore, to solve x cubed plus y cubed is equal to 20z cubed. We have to consider also, we note that x plus y is also equal to 20, which will help us. And remember from the beginning that we also have to consider the fact that y is greater than x. That will be useful probably. I don't know when. Maybe it will, maybe it won't, but might as well. And x is less than y. So what do we have? But we have from this expression here, z cubed is less than k squared, z cubed is greater or equal to k squared over 4. So that's what we've shown. So let's write that down with k equal 20. So from our deduction, we have that, and then we can write it, a quarter 20 squared will be less than or equal to z cubed, which is going to be less than 400. And hopefully this will help. So what we've got here is 20 squared is 400, obviously. So divided by 4 is 100. So we have 100 is less than or equal to z cubed is less than 400. Now we're going to use this fact and then the previous fact. Note also that z cubed is going to equal k squared. Well, k squared is 400, so it's going to equal 400, and that's going to be, let's just get back what it was we had to show. Where is it? Here. Minus 3xk, so that's minus 60x plus 3x squared. So that's going to be minus 60x plus 3x squared. So we've got a quadratic. So if we have a bound on z, we just solve this for x, and then we can sub back into our original equation. That seems like the most obvious thing to do. So let us proceed. So what can we say from here? We have that z could equal 5, 6, and if we look back at our cubes, that's a useful fact, so I don't have to calculate them. We have that 5 cubed is less than 400. So we're looking at everything less than 400. So we're looking for numbers between 5 and 7 inclusive. So we can, oops, we can write, how do we do that? Okay, let's just give it some more space. Right, so what we've got is that z is going to equal 5, 6, or 7. And we're going to test whether this equation here will be solvable in the integers for these values. So if, suppose therefore, first we should exhaust this list. There are only 3 possibilities, so it won't take too long. So suppose z is equal to 5 first. Then what we're going to get is we're going to get this quadratic. 125 is equal to 100. Subtract 60x and 3x squared. Now, that means that if we can find that this is not going to have, well, if it's not going to have integer solutions, then it's impossible for the equation above to be satisfied. The x cubed plus y cubed is equal to 20z cubed. If x isn't an integer, because if z is 5 and x is impossible because we have this expression here, which is a logical equivalent to our original equation, then what we're going to get is an impossibility. So if this isn't satisfied in the integers for a value of x, then it's impossible to solve our original equation. So let's see if we can do it. Now, what we're going to get, therefore, if we simplify it out, will be, let's see, so we have 400, let me just, it's going to be 0, and we're going to get 3x squared and then we're going to get subtract 60x, and then we've got 275. So now, one of the easiest ways of seeing whether a quadratic will have integral solutions, or indeed if the discriminant is a perfect square. Because if you think about it, when you have your formula x is equal to minus b plus or minus the square root of your discriminant, which is this, b squared minus 4ac, all over 2a. Here, this part has to be a perfect square, otherwise this is certainly not an integer. When it's a perfect square, it may or may not be an integer, but it's certainly not an integer if this is irrational, for example. So, right, let's see if this is the case. So what we're going to do is just put that to the side for a second, and we're going to see if we can find this discriminant. So what we're going to end up with is obviously b squared here, subtract 4ac, will give us our b squared. Well, this is 60 squared, subtract 4 times our a, so that's 3, sorry, I'm ahead of myself, times 275. And this, it will obviously say 60 squared, we'll keep it like that, and then we'll get 12 subtract 275. So now we're left with a little bit of a large calculation. So what we're going to do is we are going to factor out the 12, because 12 is everywhere, and then we notice that 5 is also everywhere, because there's a 12 here and there's a 5 here. So when you're trying to do large calculations, we use the fundamental theorem of arithmetic to help us that every positive integer is either prime or it's a product of primes. And that will help us greatly in solving or simplifying at least large numbers without a calculator, because we're not allowed a calculator instead. So let's do that then. So let's see, we have here a factor of 60, essentially 12 times 5 twice. Here's the 12, and there's a 5 hidden in there as a product, as one of the factors, sorry. So we're going to get 12 times 5, and then we're going to get another 12 times 5 here. We've taken the 12 away, and then we've got to divide 275 by 5. So doing that, you'll find that that's 55. So then we get this. And then what we're going to do is we're going to see, oh look, there's another factor of 5. That's great, because that's a square number, so it's looking good. And we're going to end up with 5 squared, and then we're going to end up with 12, and then 55, that's subtract 11. So what we're actually going to end up is just 12 times 5 squared, but 5 squared times 12 is certainly not a square number, because 12 is not a square number, and it is square free, in fact. Well, it's not square free, but it is not a square number, which is sufficient for us to know that this is not a square number. So, therefore, we can deduce that it has no solutions. Therefore, for z, which is not square, we should write here maybe, a square number. For z is equal to 5, there are no solutions. And this is because this is not rational even. And take the square root of this, this will be irrational. The square root of 5 squared is 5, that's fine. But then the square root of 12 is going to be, well, I'll write that, not rational, since the square root of 12 times 5 squared will be obviously 5 times 12. Well, 12 is 4 times 3. The square root of 4 is 2, so that would be 5 times 2 times root 3, which is obviously not rational. So now we're going to try our next value of z. Now try z is equal to 6. Then we will get this equation here. When we do that, 3x squared subtract 60x, add 184, and we set that equal to 0. So we now try to, sorry about that, we now try to factor this, but again we can see that when we do the discriminant on this thing, we'll get that b squared subtract 4ac is going to equal 1392. And how do I know that this is not a perfect square? Well, a perfect square can't end in a 2. How do I know that? Well, if we think about any number, take any number, we know that every number in base 10 can be written as powers of 10, and especially integers, powers of 10 added to multiples between 0 and 9. So for example, if you have 52, then that's going to be obviously your 2, this is the number between 0 and 9, times 10 to the 0, and then we add 5 times 10 to the 1. And that's by definition how we express numbers in base 10. So what we do then is we can see immediately that if the number is not a square number here, if this digit is not a square number, then this is not a square. So how do we see that? Well, we can see that by writing out any number n is going to equal summation to, let's say, k from I equals 1 of ai 10 to the I. Now if we square this, we see that what we're going to get in the unit term, i.e. the number between 0 and 10, is we're going to get, it should be 0, obviously, because otherwise this won't be 1. So we're going to get here a 0 squared times 10 to the power 0 squared plus, and that's the term there you get only with the unit term. So therefore this has to be a square number, but 2 is not a square number. So therefore, and then we don't care about the rest, this individual term here is not square, so therefore the whole number can't be square. So we can conclude therefore 1392 is not a square number. So, no solutions. Thus, no solutions to our equation. Now let z equal, which would we did? We did z equals 6 there, so we're on to 7 now. And that is going to mean that we have a new equation. We obtain 3x squared, subtract 60x plus 57 in our equation, which we will solve. And now what we can see, that this is obviously going to have a solution. Why? Immediately before trying to do anything with the discriminant, just try and look at it. You can see that 3 times 1 added to 57 will give you 60, and then if you subtract the negative 60, you'll get 0. So therefore, x equals 1 is a solution. Easiest equation to solve in one sense, that's kind of them. So what we do now is we can then factor this. Therefore, we have this expression here, subtract 60x plus 57. That will equal, well, we know that x equals 1 is the solution, so x minus 1 must be a factor. Therefore, we can conclude, therefore, we need a 3 here for the other x. And then we need, well, what are we going to get? Minus 1 times what equals 57? Well, negative 57. This clearly not an integer, because this is actually, well, 3 doesn't divide that. And so therefore we know that x equals 1 is the only one. So now what we have to do is we have to find y. We know z, so we have to find y. So if x is equal to 1, we have that x plus y is equal to 20, therefore y is equal to 19. So we get the triple, and the only triple which solves this equation which we wanted to solve as being x is equal to 1, y is equal to 19, and z is equal to 20. Excellent. Right, so now on to part 2. And part 2 may be more challenging. So what I'm going to do now is I'm going to bring down the question. Let's just copy and paste it there so we've got more context with our solution. So we've got part 2. So what we're going to do is consider the case here. Suppose now, instead of previous assumption, that x plus y is equal to z squared. We now find two solutions of star when k equals 19, and let k be equal to 19. So how are we going to solve this problem? So what we're going to do is we're going to first of all write down the equation we're trying to solve. We have x cubed plus y cubed is equal to 19 z cubed. Now, we're going to have to do a little bit of algebra here because this is going to have some sort of way to simplify. And we're going to try and find maybe some inequalities which we can use on z and therefore solve as we have done earlier, but it's not immediately obvious what to do. But what we found earlier was that writing x cubed plus y cubed as a different way did help us. And so we want some sort of factor of z squared in maybe this term. We know there's a factor of z squared here, but what we can do is we can try something at first because we're not quite sure what to do. So maybe we should just write this as a factorization out, x cubed plus y cubed. Now, what do we know? We know that if x equals y and minus y, then this will be 0. So x minus y is a factor. And x plus y, I should say, will therefore be a factor. X minus y is x equals minus y, so therefore we have a factor of x plus y. And what we get is this. And then what we can do is we can see that we need an x cubed, so we get the x cubed. And we also know we need a y cubed, so we're going to get the y cubed if we put that there. Now we're going to have an y is x squared and then y squared x. But if we put an xy here, we're going to get an x squared y, and then we're going to get that. So we need a negative value of this xy. And this is the factorization. It's something that you should try to remember, actually, in general, of some expression of the form x cubed plus y cubed, or x to the 4 plus y to the 4, etc. There are generalized formulae or expressions, identities, algebraic identities, which will help solving certain questions. Now, why did I do that? Because again, I know that x plus y is equal to z squared. So I'm making my life easier by writing it like this. Then we get z squared, and then we get x squared minus xy. And this is exactly this side. So that's useful. So we're trying to simplify, get some constraint on one of the terms, maybe y or something, or definitely z. We want to maybe eliminate y or somehow. We can eliminate y if we can find y squared, maybe that might help. So what we're going to do is just write it out like that for now and see where we can go from here. So what we can see, therefore, obviously, as I said before, this is all equal to 19z cubed, so we can actually cancel out, just get a z. So then what we can do is we get z cubed times 19, of course, is equal to z squared times this stuff, x squared, subtract xy plus y squared. So this problem would be quite hard unless you knew this identity here. Because it, in other words, step requires you to have sort of done quite a few algebraic manipulation exercises maybe, to be able to attempt a step problem, or maybe you have learnt it from another step problem. Either way, it is useful to have these identities in your head, because they will help. So then we're going to end up with something much simpler than the original part. And remember, we can divide by z because z is non-zero. Obviously, we can't divide by 0 because that would, be undefined and may lead to loss of solutions, or just bad mathematical practice in general. So now we can see we have here that we have y squared, and we have that y is equal to z squared minus y. So then if we sub that in, we're only going to end up with x and z. So that's what we're going to write here. So we get x squared, similar to what we did earlier, really. X, and then it's y is equal to z squared subtract x. So that's z squared subtract x. And it's exactly what we did earlier, really. In fact, apart from this part here, this is the harder part to spot. So let's have a look. We've got y squared now, but that is exactly z squared subtract x all squared. So then we should end up with another load of algebra to do, but we're not scared. We can do it. So let's do it. So x squared subtract x z squared. But then we've got to add x squared. And then we've got z to the 4. Oops, that's a 4. And then we've got to subtract 2x z squared. And then we add x squared. And now we see if we can cancel anything out. So what have we got? Well, this is right, this all as 19z. And then we can see if we can cancel anything. So we'll collect the terms and then we'll see what we can cancel. So we get 3x squared, because there's an x squared here. I like to put the lines through just to help me only then focus on the rest. So we've got xz squared, and then we've got another 2xz squared here. So we're going to end up with 3xz squared. And then we're going to end up with z to the 4. Now, what do we have here if we think of z being fixed? We have another quadratic. So the idea is to use that fact. And if we set this equal to 0, we're going to get 3x squared. And then we're going to get, well, I'm going to write this as 3z squared x. And then I'm going to write plus z to the 4 subtract 19z. And thinking of this as a quadratic will help us solve the problem, hopefully. This is typically where step is slightly harder than an A-level question, because the coefficients are given in terms of z, but we know that we're going to fix z at some point. So if we just think of it as a variable in x, then it's nothing but just a normal quadratic. It's just that you won't probably have seen it like that, or definitely not thought about it on your own. So, but what we're going to do though is just use the quadratic formula, and what we'll get is x is going to be equal to 3. So it's going to be 9z squared, isn't it? Because this is going to be b squared, so it's 9z squared. So I apologise. 9z squared. And they're going to have plus or minus the square root of b squared. No, it's minus b. I'm sorry, I'm getting the quadratic formula wrong. That's a bit silly, isn't it? So we're going to get plus 3z. There's a z squared. That's why I said that. I see. Yes, of course. So we're going to get plus 3z squared. And then we're going to get quadratic formula, which will give us 9z to the 4, subtract 4 times the 3. And then we're going to have this part, which is our c, z to the 4, subtract 19z. And that's all over 2a, which is 6. And so therefore, we need this expression in here to be greater or equal to 0. For real solutions at least. So therefore we need 9z to the 4, subtract, well, 12 lots of z to the 4 minus 19z greater or equal to 0. You see the common idea, you have to look at the expression you're given and think, what are the conditions? This was similar to the question 1. What are we allowed to do? What are we confined by? Well, we're allowed to do algebra, but we're confined by the fact that when we do algebra, we notice that square roots have to be positive for real solutions, and we definitely want real solutions. We want a stronger condition. We want actual integral solutions, so that's all solutions in the integers. And so what we're going to do is we're going to then write this out as, so what we get? We've got 9z to the 4 subtract 12z to the 4 plus 19 times 12. There's 12z. We need this to be greater or equal to 0. So then what we're going to do next? Well, we're going to write down, of course, what we get here, which is the positive term first. That seems sensible. 19 times 12. Notice I don't bother multiplying it out for now, because it might not be useful. No, I'll just write it like this. 19 times 12z. And that's going to then have to have this term here. Subtract 3z to the 4 greater or equal. What's going on here? Greater or equal to 0. And so therefore what we can also see then is we do this, z times our 76, factoring out z of course, and that will be subtract z cubed greater or equal to 0. Since z is greater or equal to 0, this here has to be greater or equal to 0. So that means that z cubed has to be between 1 and less than or equal to, of course, 76. Right, and the other condition is we need that this other thing, 3 times our z times multiplied, so you notice we've taken a factor of 3 out of here, but we need the whole thing to be a perfect square. So this is the discriminant simplified. 3z times 76 subtract z cubed to be a perfect square, which means it's an integer. Okay, so what does that mean? Well, it means that we have to think about this one first. So we want to think about all the cubes less than 76. Well, actually, that's fairly easy because the cubes less than 76, well, we can look at them up here. We're lazy, but we can see that they're between 1 and 4. So we've got that z is between 1 and 4, and equal obviously to 2 or 3. So we've got that z is equal to 1, 2, 3, or 4. So what we do first is we check to see when z is 1. What do we get? Well, we get that 3 times 1 is 1, obviously. And then we have 76 subtract 1, which is obviously 75. We can see clearly this is not a perfect square. No, 3 times 75 will be 225. And we have that but the only problem we have is that z squared 1 is going to equal x plus y. This is a problem though because x and y are positive integers, and so therefore this is impossible. Okay, so this is a little bit sneaky because it could be 1, right? This is a perfect square. However, we can't solve this equation. It is not solvable. Okay, so this is a little bit sneaky, but we spotted it. We know also that x has to be less than y, but y is 1 is the smallest value, and then x can't be less than y. Well, it can be, but it's not allowed to be a non-integer that's less than 1. So, or an integer less than 1 even. So, what we're going to do then is go into z equals 2. And we can see that what we get is 6 times, well, we've got 76 subtract 8. And that is equal to 408. Now using the fact earlier that the last digit has to be a square number if the number itself is a square number, we can see that 408 is not a square, but 408 is not a square number. Right, so now we're going to try z equals 3. Hopefully we'll get somewhere. Otherwise we won't find any solutions. It'd be a little bit of a shame. So let's see, 76 subtract 27. We can see that this is going to be 49 if we simplify it times 9, which is a perfect square. Is a perfect square. So this is our candidate. Great. Now before we go on and actually calculate whether we can find z and x and y, we're just going to find out z equals 4 first. So what we get is we have that z equals 4. Then what we have is, when we simplify it, we'll get 12 times 12, which is again a perfect square. Right, now then, so what we're going to do is we're going to substitute into our formula, the quadratic formula for x. If you remember, x was our formula up here. And we're going to substitute the value of z in to this equation. So x will then be given for when z is 3, we will get this 3 times 9 plus or minus the square root of 49 times 9 over 6, which ends up being 3 times 9 plus or minus 21 over 6. We can quite clearly see, therefore, that then x is 8 or 1. But we have to remember that x is less than y. And then what we get then is the triple, since x is less than y. And remember, we need to solve x plus y equals z squared, which is 9. We can do that when y is 8. We must have x is equal to 1, y is equal to 8, z is equal to 3. And we found 1, so that's great. So now we have to find the other one, which is z is equal to 4. And when we do that, we see that we get x is equal to this quadratic expression, which is 3 times 4 squared plus or minus square root of 144, obviously, and that is 6. And then what we get is 3 times 4 plus or minus 12 over 6. And we can easily simplify that to find out that we have to have, therefore, x is equal to 10 or 6. Again, since x is less than y, x plus y is equal to 16, we must have x is 6, y is 10, z is equal to 4. These are the only solutions since we're constrained by z, and then obviously that in turn constrains x. See, if x is going to have a real solution, then this has to be a square number. Let's say it's a real solution, it has to have an integral solution. This has to be a square number. But also, and some more conditions on this first one, x plus y equals 1, which was not solvable, so therefore no solutions for that one. Then no solutions for this one, so that's not a square number. But then these ones correspond to two square numbers. So we have exactly two solutions, x equals 6, y equals 10, and z equals 4. And the other one was x equals 1, y equals 8, and z equals 3. So quite a lengthy question there, but we managed to get through it. And so what we've learned from it? Well, we learned that we need to be quite good with algebra for STEP. Okay, we need to be able to think how to write something differently. That's what I was saying. If you connect ideas 1 to 2, that's one thing, but you've got to be able to connect it to 3 via 2, if that makes sense. So the idea here is that x plus y cubed is being connected to 3 backwards. So we're going 3 back to 2 back to 1. In other words, we're solving this problem by thinking, how can I relate two things I don't know any relation while I relate them via something I do know. And that is this x cubed plus y cubed can be written like this, x plus y all cubed. Therefore we get this k cubed. And that happened again later when we wanted to simplify. We had to write this x plus y, which is z squared, and then we can cancel by z squared, so we just get a z, and then we can easily substitution. We've got our second condition. So there's two things to think. You have to think good algebra, and then secondly, in this problem, you had to be using the things that you were given. Right? So you've got this expression x plus y equals k. Well, you're probably not going to use exactly directly that. What we did here, actually, x plus y, well, in other times, x plus y was k. We used that up here, x plus y. But we won't have to substitute so that we have x is equal to k subtract y, or the other way around. Y is equal to k subtract x, and substitute that in for y. Great, well I hope you enjoyed that video, and so if you did, then great, and I'm glad that I've helped. So thank you for watching, and see you next time.